Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 4 from lesson 6-7 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to talk about the formula for the sum of a finite geometric series. Whoo, boy, that's quite a quite a title, isn't it? So I just want to explain a couple of the words here. So sum is adding. When we talk about a finite series, finite means it doesn't go on for forever. So, remember, a sequence is just a list of numbers. We're going to have just a certain amount of those numbers. So we might add the first 5 or the first 7, something like that. Geometric series. So geometric means that to generate the list of numbers, they're multiplying by the same value over and over. And when we say series, we're adding together the numbers in that list. Alright, so what we're going to do is we're going to generate a list of numbers of a certain length, and from one number to the next, it's multiplying to make that next number, and we're just adding them together. Alright, so we have this formula here on the right that's going to help us, and it looks like quite a doozy, doesn't it? So I just want to point out this is actually two formulas written together as one. Here's my first one. And here's my second one. But I specifically want to show you how to use those. So on this left-hand one, I know that this has an explicit formula in here. But I'm going to call this the recursive side of the equation. So what we have is we have this E symbol here. That is the Greek letter sigma. And so what the Greek letter sigma does is it tells you to add together the certain number of terms. That's why this is recursive, is because this sigma here is telling you to take these values and add them. Alright? And the bottom number down here where it says I equals 1, that's telling you to start with the first position and to go up to whatever other number we have. So whatever number n is, that tells you how many blanks we have. So for example, this is telling us to find the first 7 terms. So this left-hand side of the equation that I boxed in yellow, that is really how we generate the list of values, or how we write the expanded form of the series. Now remember, a series means that I'm adding together that list of numbers. And so adding those numbers can sometimes get really ugly. Okay, if it's like these hideous fractions, which you're going to encounter in just a second, you're going to be like, ain't nobody got time for that. So this right-hand side of the equation is kind of our way of explicitly doing that. So without needing to generate the entire list and add them one at a time, this will find the value for us, essentially. So let's go ahead and let's do part B here. So part A specifically says, how can you find the sum of this series? And to answer that a little more thoroughly is you can either use the left-hand side of this equation to generate a list and just add those together, or you can use the right-hand equation to just immediately get the sum. Alright, in these examples, I will actually end up doing both ways for you. So for part B tells us first to write the expanded form of the series. So if I look at this, I need to generate 7 numbers, because I'm going from slot 1 to slot 7, which start with n equals 1. Now I can generate these numbers in 2 ways. The first way is what you're a little more familiar with, is, oops, that's a 7. So the first way, you guys are familiar with identifying the first term in a sequence when you look at a recursive formula. Remember, this is your initial value. which really means the first blank. And this is your common ratio. So you guys are used to taking the initial value, multiplying by the common ratio, multiplying by the common ratio, multiplying by the common ratio. You guys can do that. In fact, I find that's easier. And that's what I would do. So 3 times 2/3 is 2. 2 times 2/3 is 4/3. 4/3 times 2/3 is 8/9. So see, that's easy. Now the other thing that you can do is you could take these n values and actually plug them in. So I would do 5 minus 1 is 4, so 2/3 to the 4th, and then times that by 3. And it's a few more steps, but you could. Or you just keep doing what I'm doing. So 8 times 2 is 16. 9 times 3 is 27. 16 times 2 is 32. 27 times 3 is 81. Either way, that's the expanded form. Now, to make it a series instead of a sequence, you separate those with pluses. So there is my series. Now, to find the sum, I have two options. I can add together all these fractions, which would suck because they aren't all written with a common denominator. Or I can use this right-hand side of the equation, which is also going to suck, but in a different way. So let's go ahead and try that just so you can see how to use the formula. So I have S sub 7 is equal to my initial value, which is 3, times 1 plus my common ratio, which is 2/3, raised to the n, which is the top of the sigma, 7th power. Now notice that 7 is only applying to the 2/3. It's not applying to the 1. So like, I made this goof a little while ago. Oops, that should be a minus. I made this goof a little while ago. I tried to cancel the 1 minus 2/3 out from the bottom. But you can't because this one has an exponent there. Womp womp. So now let's simplify this. So first I'm going to take the 2/3 and raise it to the 7th power. So 2 to the 7th is 128. And 3 to the 7th is 2,187. Now, I know I'm subtracting that from 1, so I'm right away going to write my 1 to match that denominator. And downstairs, 1 minus 2/3 is 1/3. So now my next step, when I divide by 1/3, that's the same thing as multiplying by 3. So 3 times 3 is 9. And then I'm going to go ahead and deal with this ugly top part. So 2,187 minus 128 is 2,059 over 2187. So I just combine those fractions. Ooh, and I don't know if I'm going to be able to squeeze this down there, so I'm just going to write it to the side. Sorry for my junky positioning. But if I do 2187 divided by 9, I get 243. So 2059 divided by 243. So that's my exact solution, which is cool. Savvas gives us that exact solution. You could pop that right on into Desmos if you wanted, this hideous thing right here, and you would get approximately 8.47. So it really depends on how the book is asking for a solution. If it tells you to round it to the nearest digits, don't do all this arithmetic, just plug that into Desmos. But if they ask for an exact solution, well, you're going to trump your way through that, okay? So let's try this again. Let's do the try it. All right, and it's going to have us do this bad boy twice. For the sake of space, I have the feeling I'm going to need the space, so I'm going to write it like this. Sorry for rearranging you. Alright. So first, part A wants the expanded form of the series. Now notice it goes from 1 to 5. So I want the first 5 blanks. Now normally we don't write these blanks in here, but I feel like it makes it easier for you guys to see. So there it is. Now my a sub 1 here is 1/2, and my common ratio is 3. So to generate the next numbers in the sequence, I would just multiply times 3. So 1/2 times 3 is 3/2. 3/2 times 3 is 9/2. Then 27/2, and then 81/2. Now, Lord, y'all, check out this part. It says, what is the sum? So remember, a series all has to be added together. So part of you guys are groaning and going, no, I don't want to use that ugly formula. Why? Why me? And then you cry a little. We'll be honest, here we don't have to use that formula. If we know what our list of numbers are, and they're not annoying to add, right? These all have a common denominator of 2, so adding them really isn't that bad. So to find the sum, just add all those together. We know the denominator is going to be a 2 because that's the common denominator, but just take 1 plus 3 plus 9 plus 27 plus 81 and add them. You get 121. If you used that really, really crappy formula that we just did, you would get the same thing. It's just a lot more work, and we're kind of lazy. Alrighty. Now part B. Part B stands for I don't want to do it, but here we go. So this one wants us to write the series. So it's actually asking us to write the equation in sigma notation. Now remember, sigma notation starts by having n equals 1, and it goes to some number up here. But the thing is this says plus ... so I don't know how many terms are between here. Is this the 20th term? Is it the 3rd term? Is it the 12th term? Who knows? So we're actually going to have to solve to figure out what n value goes up here. But we'll get there. Give it time. Now after our sigma here, what we need to do is we need to go ahead and write the equation with the explicit formula, right? So I need my starting value times the common ratio raised to the n minus 1 power. So my starting value is right here. It's just the first number in my sequence, which is -2. And then to get my common ratio, I just divide the -2/3 by -2. And I get 1/3 as that common ratio. So my last thing is now to figure out what that stinking n is. So what I'm going to do is I'm going to take that -2 over 243 and set it equal to that explicit formula. And notice that the only variable that's missing is that n. So to get the n out of the exponent, I know I'm going to need a logarithm. But I can't take a logarithm when there's something multiplied to this exponential. So I need to divide by the -2 to get the exponential alone. So on the left-hand side, I have 1 over 243. And on the right-hand side, I have 1/3 to the n minus 1 power. And now I'm ready to take that log. Now remember, if ever you take a log, you need to make sure that the base of your log matches the base of your exponential. So this is the log base 1/3 of 1 over 243. Now understand that 3 to the 5th power is 243, so this logarithm simplifies to a 5. You could plug that into some fancy schmancy calculator and get that same thing. Okay. Now my last thing here, to get n alone, I add the 1. So my n value here is 6, and that's what goes right there. So there is that series in sigma notation. Now, Lord Almighty, now they're asking us to find the sum. I don't want to. I don't want to do it. I'm going to do it because I need to do it, but y'all, I don't want to do this. I know I'm going to need more room because this thing takes up all kinds of space. It won't be so bad, though. Here we go. So I'm just rewriting this part of the equation, filling in our values. So I'm finding S of n. So I have S. Now my n value is the top of the sigma, which is 6. So I'm finding the series, the sum of the first 6 terms of the series is what that says. Equals a sub 1. So my initial value, which is -2, times 1 minus my common ratio, which is 1/3. And that common ratio is to that 6th power. All over 1 minus that common ratio, which is 1/3. Oh boy, here we go. Now down below, 1 minus 1/3 is 2/3. And so what I'm actually going to do with that 2/3 just right away, because I know I don't really have much room. When I divide by 2/3, that's the same as multiplying by 3/2. So -2 divided by 2/3, or -2 times 3/2. The 2's cancel out, and that turns into a -3. Alright, so I did some mental math there. Lord help to those children who need to go ahead and actually read the notes on this. Hopefully they'll figure it out. I'm going to put a couple of hints there. I'm going to call that 2/3. And then I'm going to put some coloration here just to tell them to look over there. Okay, hopefully that kind of leads them along. Alrighty, so now we got to do the ugly part. So we're getting there, y'all. So the series, part 6, I have -3 times, and now I'm just doing the 1/3 to the 6th. We'll get to the 1. I'm not worried about him yet. But the 1/3 to the 6th I'm worried about. 1 to the 6th is 1, so that numerator's not too ugly. And 3 to the 6th is 729. Now I know that I'm doing 1 minus that, so I need my 1 to have a common denominator. So I'm rewriting 1 to be 729 over 729. And when I do that subtraction, I get S sub 6 equals -3 times 728 over 729. Ooh, gotta get real skinny here, y'all. We're gonna fit it here. I know that 3 is going to cancel out with some of the 3's down here, right? So I'm doing 729, taking that back a notch and dividing it by 3. So I get -728 divided by 243. And there's my sum, and it's ugly, y'all, and that's okay. So there you have it, guys. That is the formula for the sum of a finite geometric series. Until next time.